Hi, my name is Susan Steele-Dunne from TU Delft. Here I'll present results from a recent study that I conducted as an EUMETSAT visiting scientist at TU Vienna. The goal of this study was to improve the representation of the vegetation in the TU Vienna soil moisture retrieval approach, and in particular to focus on including dynamic vegetation parameters to account for interannual variability in the vegetation effect. Before I start, I'd like to thank EUMETSAT for supporting this research and TU Vienna for hosting me and their collaboration on this project. ASCAT data are used to produce the longest standing operational soil moisture data service in the world. These soil moisture products distributed by EUMETSAT are based on observations from the advanced scatterometer ASCAT. There are currently 3 ASCAT instruments in orbit on METOP A, B, and C. The ASCAT instrument builds on the heritage of the scatterometer flown on ERS 1 and 2, and the future launch of METOP second generation ensures that there will be data from a C-band scatterometer until at least 2030. This is strong motivation to continue to develop and improve the soil moisture products based on ASCAT data. The TU Vienna soil moisture retrieval algorithm is the basis for several kinds of soil moisture data sets distributed via the EUMETSAT HSAF. The algorithm is used directly to produce real-time surface soil moisture products at 12.5 and 25 kilometers. It is combined with data from ASAR to produce a 1 kilometer surface soil moisture product, and the ASCAT soil moisture data are assimilated by ECMWF to produce soil wetness profile data, and also a long-term data record stretching back to 1992. In the TU Vienna soil moisture retrieval approach, the backscatter in decibels is assumed to be linearly related to the surface soil moisture. Soil moisture in the surface layer is given by this expression, where sigma naught is the backscattering coefficient at some reference angle, and sigma wet, sigma W, and sigma D are the wet and dry references at that instance angle. The wet reference is indicated in blue in this figure. This is the upper limit of backscatter, or the highest value that backscatter reaches at that location. The dry reference is shown in green. This is the backscatter corresponding to dry soil. During the winter months, the backscatter from dry soil depends on the soil texture and roughness. During the growing season, the dry reference is higher because it's also affected by the backscatter from the vegetation itself. The difference between the wet and dry reference is the sensitivity of backscatter to soil moisture. And so sensitivity is highest over bare soil during the winter months. Sensitivity to soil moisture is at a minimum when the biomass is at its peak. The parameters required to estimate the dry reference, the slope, and the curvature are calculated using ASCAT's unique viewing geometry. ASCAT has 3 antennas on each side at 45 degrees, 90 degrees, and 135 degrees to the satellite track. We can use those to characterize the incidence angle dependence of backscatter. In general, we assume that a change in soil moisture results in a shift of this curve, and a change in the vegetation cover leads to a rotation or a change in the slope and curvature. So we can use the incidence angle dependence of backscatter to account for the effect of vegetation on the dry reference. Each antenna observes the surface at a range of incidence angles. So any location on the surface is observed with 3 antennas in quick succession. So it is observed almost instantaneously at 3 different incidence angles. This gives an estimate of the incidence angle dependence that we call the local slope. However, these data are very noisy. In order to obtain a robust description of how the backscatter varies, we need to combine many values of the local slope. When this change detection approach was first applied, the incidence angle dependence of backscatter was accounted for using empirical seasonal cycles that varied per vegetation type. When ASCAT data became available, the increased data density meant that the relationship could be estimated from the observations themselves. The entire data record was combined to provide an estimate of the slope and curvature, and hence the dry reference for each day of the year. In this study, this approach is referred to as the climatology approach. This is the approach used operationally to generate the soil moisture products distributed by EUMETSAT. In the current study, we're working towards the inclusion of dynamic vegetation parameters, So rather than have a single value for a given day of the year, the idea is to combine data in a moving window so that we can also include interannual variability. This approach was proposed by Meltzer et al. In 2013. So an Epinechnikov kernel is used to combine local slope values within some window so that the weights are highest on the day of interest and fall to zero within some time frame. Meltzer suggested a kernel half-width of 21 days, and so that is our starting point too. In this study, we'll investigate the benefit of using dynamic vegetation parameters compared to climatology, and we'll consider the impact of this kernel width. We've conducted this study using 10 years of ASCAT data at the sites of the United States Climate Research Network. Data from this network of 109 stations were obtained through the International Soil Moisture Network. Within this area, there are 8 different ESA-CCI land cover classes and 14 different climate classes. Some stations were omitted. The desert shrubland locations in the west were excluded because we observed what looks like enhanced volumetric scattering. We also excluded stations within ASCAT footprints that include water or are flooded. And we excluded stations that occurred in climate or land cover classes that were found at fewer than 5 stations. So in the end, results will be presented from an analysis of 85 stations. The maps in the top row show the performance of the current version of the TU Vienna soil moisture approach, i.e. using climatological values of the slope and curvature. Performance is actually pretty good. The median Pearson correlation coefficient is 0.58, with values up to 0.79. Values are highest in the central US and lower in more arid areas. The mean unbiased root mean square difference is 0.09% volumetric, and the median bias is just 0.01%. Negative values of bias were more common in the west, while positive values were more common in the east. The bottom row shows the performance metrics binned by land cover type. The best performance was in grasslands, class 130, where R was generally higher than 0.5. The unbiased root mean square difference was among the lowest values observed, and the bias was close to 0. Similar good performance was observed in croplands in terms of R and unbiased root mean square difference, but there was a wide range of bias values. As expected, the performance is quite poor in broadleaf deciduous forest, class 61. Though the bias is close to 0, R is relatively low, and unbiased root mean square difference is higher than in the other classes. But all in all, the performance of the current approach is really quite good. It's also quite reasonable to expect that the performance will be better in less dense vegetation. So what happens when we implement the dynamic vegetation parameters? First, let's take a look at the dynamic vegetation parameters themselves. On the top, you can see the slope in orange and the curvature in blue, estimated over a 5-year period. If we use climatological parameters, this will be a periodic signal repeating every year. Using the kernel smoother, you can see that the seasonal cycle is slightly different each year. There's no long-term trend here in Stillwater, but there is certainly some interannual variability. On the bottom, you can see that this introduces interannual variability in the wet and dry references. The wet reference doesn't change so much, but interannual differences in phenology produce differences in the dry reference. So the sensitivity to soil moisture now also has some interannual variability. Including interannual variability can be beneficial. This is an example to show when this happens. At the top, you can see that the dry reference has a very strong seasonal cycle and limited interannual variability. The Pearson correlation for the climatology case is already 0.82, and being able to account for interannual variability only increases it to 0.83. In the lower plot, though, you can see that there is a downward trend in the maximum value of the dry reference. This is not accounted for in the climatological values, and so including dynamic vegetation parameters increases the Pearson correlation coefficient from 0.69 to 0.73. Now let's take a look at the impact that the dynamic vegetation parameters have on the performance metrics overall. Over the whole domain, the median change in Pearson correlation coefficient was 0. While some increase in R was observed in the West, generally it decreases in the central US. Furthermore, introducing dynamic vegetation parameters actually made the unbiased root mean square difference and the bias slightly worse. The spatial patterns can be explained if we look at the land cover in the bottom row. Generally, the increase in R is seen in the shrublands in the West. We can see that the difference in unbiased root mean square difference and bias is greater than 0 in all cover types. The increase in bias is actually worse in the croplands and grasslands, which is where the operational algorithm does best. So why would including dynamic vegetation parameters make the estimate worse? This figure shows the soil moisture at Stillwater, Oklahoma at the top, followed by the slope and curvature and the dry reference at the bottom. The gray lines are the values estimated with climatological values of slope and curvature. So these are used in the operational algorithms. You can see that these are quite smooth, so they capture the seasonal cycle due to vegetation. But remember that these are the same every year because they're based on the entire data record. The slope and curvature are both smooth, so the dry reference has a nice smooth seasonal cycle, accounting for the vegetation phenology. The blue lines correspond to the parameters estimated using a kernel smoother with a half width of 21 days. In terms of the overall seasonal cycle, there are some differences with respect to climatology, but you can also see that it's less smooth. There are some short-term variations that are not apparent in the climatological values. If we make the kernel window even shorter, so look at the orange curve, we see more of these high frequency variations. If we make the kernel window longer, so look at the green curve, you see that they get smoothed out. So the reason why the climatological values do so well is that they do a very good job at capturing the seasonal cycle of the vegetation. So while introducing dynamic vegetation parameters allows us to capture interannual variability, it comes at a price because we become sensitive to these high frequency variations that are basically averaged out in the climatology approach. It seems like the kernel width is important. So what is the effect of making the kernel window longer or shorter? In general, using a shorter window leads to a decrease in R and an increase in unbiased root mean square difference and an increase in bias. Increasing the kernel width led to a lower R in the West, but an increase in the central and eastern US. In the more humid areas, using a longer kernel width leads to an improved performance. If we look at the impact with respect to climatology, we see that as we increase the kernel width, we're basically just approaching the performance of the climatological approach. As lambda increases, there's a small increase in R with respect to climatology, and the difference in unbiased root mean square difference and bias go from being detrimental to having no impact. So if we want to use dynamic vegetation parameters, we should use a longer window to filter out these high frequency effects. So what we've learned from this study is that the current approach based on climatology is very robust. When we combine local slope values over the whole data records to get a seasonal cycle, we capture the incidence angle effects that are really due to the vegetation phenology. The primary control on the performance of the retrieval algorithm is the fundamental sensitivity of backscatter to soil moisture, which is determined by the vegetation cover. Performance is very good in grasslands and croplands where there is vegetation cover, but still some sensitivity to soil moisture. If we have a lot of interannual variability in vegetation cover, it can be beneficial to estimate the dry reference using the dynamic vegetation parameters. So the dynamic vegetation parameter approach could be beneficial if there's a trend, like a loss or a gain in biomass over time. And it could also be beneficial if there's some variation in the timing of the seasonal cycle. However, using the dynamic vegetation parameters makes our estimates more sensitive to short-term influences on the incidence angle dependence of backscatter. In the TUVN approach, we're accounting for the influence of seasonal variations in vegetation cover, affecting the sensitivity to soil moisture. So we're accounting for a loss of sensitivity to soil moisture due to the attenuating effect of the vegetation, and also the fact that there's backscatter from the vegetation itself. When we apply a kernel, we become sensitive to the individual data points. So we become sensitive to short-term confounding influences that are less well understood. So for example, we need to have an improved understanding of the influence of interception and dew. What we need to focus on in the long term is understanding the physical processes behind these short-term fluctuations and finding a way to mitigate their influence on the soil moisture retrieval algorithm. One workaround would be to filter the local slope values before we apply the kernel smoother so that we exclude any unwanted confounding factors. In the longer term, it's always worth understanding these factors so that we can ensure that the way that they are handled is correct. A detailed description of this study and a closer look at the results are provided in this journal article, which is openly available. If you have any questions or ideas, you're very welcome to contact me via email or to follow this research on our website. Thank you.